Survey of Calculus, Chapter 1, Section 8, Higher Order Derivatives. Okay, so let's consider this function. We have x to the fifth minus 3x to the fourth plus x. The derivative, 5x to the fourth minus 12x to the third plus 1. Well, we can also take the derivative of the derivative. In other words, the derivative can be differentiated. We can think of the derivative of f prime as the rate of change of the slope of the tangent lines, or it could be regarded as the rate at which the derivative f prime is changed. So we use the notation f with two slash marks, two little quotes, for the derivative of the derivative. In other words, f with the two little marks is the derivative of f prime of x. We call it the second derivative of f. So for the equation we're talking about, we said that the first derivative was 5x to the fourth minus 12x to the third plus 1. The second derivative would be 20x to the third minus 36x squared. In other words, you just take the derivative of the first derivative. Now, continuing in this manner, we have the third derivative, which would be 60x squared minus 72x. The fourth derivative, which is 120x minus 72. And the fifth derivative, which would just be 120. By the way, the sixth derivative would be 0. Now, this notation gets a little bit long, as you probably noticed. So after the first couple of derivatives, we start to use a little different notation. And we will do an f, and then up in parentheses, what looks like a power, but it's not, will be a number, and then x, and that will indicate the derivative. So an f with a 2 there would be a second derivative. Now, Leibniz notation would look like this. It would be a d2y over dx2. It's not really squared, so I don't want to say squared. They're not powers. Or you could put d dx of dy dx. You read it the second derivative of y with respect to x. And again, the 2's are not exponents. They're not powers. So, try not to get that confused. So, if y equals x to the fifth minus 3x to the fourth plus x, then we have all of this. dy dx is 5x to the fourth minus 12x to the third plus 1. The second derivative, and there's the notation. You see the different notations for second, third, fourth, and fifth there using Leibniz notation. What I want you to do is take y equals 1 over x and find the second derivative. You've got to find the first derivative first in order to do this. Pause the recording, give this a try, and resume to check your answer. So the first derivative is going to be negative 1 over x squared. And then we can write that as negative x to the minus 2 to help us with the second derivative. And we get 2 over x to the third. Now, this one's a little more complicated. So we got a chain rule or an extended power rule going on here. Find the first and the second derivative. Pause the recording, give it a try, and resume to check your answer. Okay, the first derivative is not too bad. It's going to be 20 times x squared plus 10x to the 19th times 2x plus 10. And then they factored a little bit. They pulled that 2 out to kind of make it a little bit shorter. You don't really necessarily need to do that. So they have 40x squared plus 10x to the 19th times x plus 5. Now, in order to do the second derivative, you're going to have to use the chain rule. You're going to have to do the product rule, and you're going to have to use the extended power rule. So, what that looks like. Remember, the product rule is the first times the derivative of the second plus the second times the derivative of the first, and it gets really messy here. You can see all the things you have to do to get it down. They did a little factoring. You probably won't have to go quite this far in homework, and you may not have one this involved. But just to give you an idea, they can get a little messy. Okay, here's a quick check. Why don't you try these problems? Give it a go. Pause the recording while you're doing it, and then resume the recording to check your answer. Okay, here we have the answers for part A. The first one, you get negative 72x squared plus 6 for the second derivative. For the second problem, we get 24x over x to the fifth for the second derivative. And for part 3, we get 108x squared plus 12 for the second derivative. And then for b, we get that the fourth derivative is 24 over x to the fifth. A couple definitions here. You may be wondering, well, why in the world would we take a derivative of a derivative anyway? What good is that? Well, you actually can use it in a lot of different areas. One area that's really popular that we use a lot with calculus is in the area of speed, velocity, and acceleration. Now, the velocity of an object, velocity is the change in distance over the change in time. So it's the derivative of the position equation. It's the limit as h goes to 0, or the derivative of the position function. A sudden change in velocity, or an instantaneous change in velocity, is an acceleration. So your original equation would be your position equation. The first derivative is velocity, and the second derivative is acceleration. And in case you're wondering, a sudden change in acceleration, which would be the third derivative, would be jerk. All right, so here's an example using velocity and acceleration. We have a position formula. S of t equals 4.905 t squared. You've got a stone dropped from a cliff. We're going to assume air resistance is negligible, so we don't want to throw any extra stuff into the problem. We want to know how far has the stone traveled 5 seconds after being dropped. You're not going to do anything but use the formula there. How fast, there's your velocity, is it traveling 5 seconds after being dropped? And what is its acceleration after it's been falling for 5 seconds? So, pause the recording, give this a try, and then resume to check your answer. Okay, A is pretty simple. You're just going to put in 5 for t, and you get that after 5 seconds, it's gone 122.625 meters. For part B, you need to take the first derivative of the position formula, and you get 9.81 t. That is the velocity. Put in 5, and you get that it is falling at a rate of 49.05 meters per second. And then the acceleration, well, take the second derivative, you get 9.81, and that is the acceleration because t has gone out of the equation, so it's just a constant acceleration. Let's look at this on a graph. Kimberly leaves her home, which would be distance 0. Remember, distance is the y-axis here, and time is the x-axis. So at 0, 0, she's at home for a 2-hour bicycle ride. The graph for distance traveled with respect to time is shown below. Find at which interval she's traveling at a constant velocity, when she's accelerating, and when she's decelerating. What you're going to need to do is remember the relationship between position, because what you have here on this graph is a position. You have a position graph. Velocity is the derivative of position. So when you're looking at her velocity, you're going to need to be visualizing the slopes of the tangent lines. And then for acceleration, you're going to need to look at the changes in velocity. Okay, pause the recording, think about this, see if you can do it, and resume the recording to check your answer. So she's traveling at a constant velocity when the slopes of the tangent lines do not change, or when the graph is linear. So that's going to be from point 2 to point 3, point 4 to point 6, point 8 to 1, 1.2 to 1.5, 1.6 to 1.8. So those are the intervals in which her velocity is constant. It says that note in the intervals 0.4 to 0.6 and 1.2 to 1.5, the slopes of the tangent lines are 0, which means she stopped. Her velocity is stopped. Kimberly is speeding up during intervals 0 to 0.2, 0.6 to 0.8, 1.5 to 1.6. It's an upward bend in the graph. And then you have the intervals there where she's slowing down, which is a downward bend in the graph. Okay, now we're going to go back to our smartwatch question from the last section. We found this derivative in the last section, and they want us to find the second derivative and then calculate it at 52 and 208, just like we did before with the first derivative. Pause the recording, give it a try, and resume to check your answer. Again, this is kind of a hairy problem to work your way through. We got to use the quotient rule and the power rule. So we have the first, or the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. When we do the derivative of the denominator, we're going to have to use our extended power rule. So you see that there. And then they did factor out the 2t plus 1 squared and canceled it, the denominator, and simplified to get negative 2 million t plus 500,000 over 2t plus 1 to the fourth. When we put in 52, we get negative 0.851, and when we get 208, we get negative 0.014. So it's telling us, let's see, it says after 52 weeks, the rate of sales is decreasing at negative 0.851 units per week. In other words, even though they increased during the 52nd week, the rate at which the increase is decreasing. So we're measuring the rate of the increase, which is getting lower. They're increasing, but not as fast as before. And then at 208, we get negative 0.04. They've nearly leveled off, so they're still increasing, but like I said before, everybody's got a smartwatch by now, or most of the people are going to get one, have one. Sales are slowing, and the increase is almost zero. Okay, here's our section summary. Pause the recording to look over this, and then resume to do the additional practice. Here are additional practice problems. Pause the recording to try them, resume to check your answers, and do this until the end of the recording.